And I will introduce Alan Whinery from the University of Hawaii, and he is going to be talking about where packets go. So take it away, Alan.
Thanks, Jason. Thanks for pronouncing my name correctly. I don't really notice when people don't, but so when I wrote the abstract that Jason sent out on Monday, I had absolutely no slides. So these slides were swept together in order to try to meet the dream of the abstract. But I think they get there pretty clearly. Now all I have to do is get the right focus so I can advance the slide. So I've got this term per-packet-provenance, and there's probably a better word than provenance, but alliteration is charming. And what I mean is, instead of just saying there's packet loss somewhere in a path, you actually find out what happened to the packets. You determine the final resting place of packets that were non-delivered, and et cetera. And generally looking at the actual, like the nitty-gritty, the detail, the ground truth is a popular term in academia lately. A larger inquiry about what you have to account for to understand the difference between your path and an optimal one. And there probably is a difference between your path and an optimal one. So part one is about end hosts and looking where packets go in end hosts. And the rabbit hole, this particular rabbit hole, there are many, originated during a troubleshooting scenario when I posed a question actually on a Perf Club call. What's the best way to invoke UDP tests without losing a bunch of packets at the sender and or the receiver? Because historically, the defaults for NUTTCP and iPerf haven't been very effective for UDP tests. You have to know stuff in order to run a successful big throughput UDP test from point to point. And typically running bigger streams requires more host buffering, and I'm not sure it would be easy to make defaults that would handle it better, but there's secret knowledge you have to absorb. So in order to kind of investigate this, I ran a test matrix of increasing rate requests and increasing buffer requests on NUTTCP tests to begin with. I did 4,608 UDP tests with NUTTCP 8.1.4. The test that I ran with 8,948 byte payloads had less packet loss than those running with 1,500 byte payloads. MTU was set to 9,000 for all tests. I just varied the UDP. I'm trying to think of the right term. The length. I varied the UDP packet length with the controls in NUTCP. Send side CPU was higher than receive side CPU, which I thought was kind of interesting, but almost all packet loss occurred on the receive side, either as an Ethernet driver Q drop or as a UDP in error, which is reported by the Linux kernel. So also increasing sender TXQ length exacerbates receive side loss. So you push harder by increasing the TXQ length. You lose more packets on the receive side. Increasing the receiver Ethernet driver receive ring buffer reduces RX miss error loss, which is what the IXGBE driver calls it. And then increasing the UDP mem control knobs in the kernel can reduce the UDP and error loss. And those are actually the same buffers that you're manipulating when you ask NUTTCP for more buffer. You actually ask NUTTCP or iPerf for more window, but with UDP, calling it a window is a little bit of a misnomer. So I did a whole bunch of heat maps, and heck, did I put that link in? Yes. That link at the top of the slide leads to the full explanation, which I'm not going to do today, or a different explanation anyway. So on these heat maps, Vertically, you've got an increasing number request for buffer. Horizontally, you've got an increasing request for throughput or for rate. The lack of loss is black, and non-zero loss is blue at very low levels to kind of kickstart it, so you don't have very, very, very dim low loss that you can't see. And you can see that the heat map on the left is 1500 byte payloads, and there's a certain amount of loss, not very big loss, but there's a certain amount of loss occurring as you increase the rate. And then when you at high rates, as you increase the buffer ask. And then on the right is the large packet version of the same thing, which is largely blank. There was a few loss, and these might be, you know, just the luck of the draw, stochastic loss or something. Another good question is, there, as I said, most of this loss is on the receive side. Well, where do things get lost? So this is the same set of tests being looked at, and this black is zero loss and blue is 0% of a lossy result, meaning on the left-hand side, you see there's a bunch of blue at the bottom. So those were lossy results, but they were not lossy results that were lost by the focus of this heat map. So there's blue at the bottom on the left, there's red at the bottom on the right, meaning that the right is where those particular tests lost their packets. So on the left, the ether received Q drops, the Ethernet driver dumped packets. It's more responsible for the high rate stuff as you climb up the buffer ladder there. And then on the right, you can see that most of the low buffer loss happened when we didn't have very much buffer. Of course, it was in the Linux kernel UDP in errors, and of course, on that graph, the vertical is the very same number that you're asking for UDP buffering. So when you have less UDP buffering, you get more loss in the UDP stack. Surprise, surprise. So, but another interesting wrinkle is these are NUTTCP graphs, and these are the same set of tests run with iPerf3. So the two programs act very differently in terms of this UDP loss. For some reason, iPerf3 loses nothing on the Ethernet driver side, and all of the loss. In fact, a lot of significant loss with the same specification. I'm sure if the iPerf3 developers got a hold of me, they'd give me a better way to run iPerf3 or something, and it might get less loss. But with using the same mindset as I was running NUTTCP tests with iPerf3 at the time, there was a lot of loss. So both at 1500 byte payloads. I should say these two where you compare the driver stack, that's all 1500 bytes because that's where the loss was. So some lessons to learn from this exercise. It's very useful to know how to look at your endpoints for packet drops. The ETH2 minus S nstat, which is better than netstat, but if you only have netstat, you could also use netstat. And then there are procnet SNMP, perhaps some other things. Ethernet drivers are notorious for non-consistent ways to describe stats. You can probably find two Ethernet drivers that are reporting the same name with different numbers, and there's a kind of a lack of consistency. And if you really want to know what a number means, sometimes you end up reading the driver source code. And it's kind of the same for the Linux kernel, but I have found that if you look for Rami Rosen, who's a professor at the University of Haifa in Israel, he does some really good lectures and some really good PDF and slide decks about what's actually going on, like the nitty-gritty inside the Linux kernel. And I found it to be pretty helpful at times. Okay, so part two. This is like one of those Hollywood movies, it's several vignettes about different things that turn out to be interrelated at the end. So this is a troubleshooting scenario. We had a 10 gig link to Seattle. We're seeing some packet loss across the link towards Seattle, hard to isolate, hard to reproduce. There would be packet loss, and then you would go and you look again, and there would not be packet loss. And over a period of some months, we fiddled with it and we looked for it, and various people got involved. And at one point, University of Washington volunteered that there was something going on with the brocade, so we all blamed the brocade for a couple months, and turned out to have nothing to do with our problem. And but then Jared Brown from Global Knock made the observation that the packet loss was very rare at MTU 1500, but damaging at MTU equals 9,000. And pinging, you can do all the pinging with the require no fragmentation that you want, and no indication that there was a path limit on MTU. So in the end, the MTU thing didn't really turn out to be that helpful. But so this is a simplified diagram of what we were looking at. So when this infrastructure, when this link was built, the MX480 on the left was actually a Juniper M120, and it didn't have the facility to work with layer 2, layer 3 stuff in the same way that an MX480 did. So that's why there's an EX4500 in there to insert VLANs after the router interface. And we had actually fixed the EX4500 at one point. It was dropping packets, and then with a 2-port 10 gig through, so there wasn't any reason to overflow queues really, but it had a problem which was fixed by reconfiguring it, reconfigured and rebooted. So then we started having this, which looked very similar, or started noticing this, and it looked very similar, so we focused on the Juniper EX4500. And I was looking at interfaces, and this interface was receiving pause frames from the Pacific Ocean. And so that was kind of the watershed moment. And then what followed was not a sequence of troubleshooting decisions, but more like brute force permutation. And it was Chris Zane who finally decided we would just unplug the EX4500 and plug the link directly into the MX480, and the packets went away, or the drops went away. So we put everything back together because we weren't ready to extract the EX4500, and we turned the reception of flow control, or acting on flow control pause frames on, and all of a sudden the EX4500 had Q drops. So in turning on flow control, we absorbed the Q drops from the next box, which turns out was the ONS. So the Cisco ONS, of course, it has LAN-PHY on the left side and WAN-PHY on the right side. And so it has approximately a 3% line rate reduction and a shallow queue, which I'll get to. So in the end, we did take the EX4500 out, and the ONS now feeds flow control pause frames to the MX480. So this slide needs to be in a different place in the presentation, but so I can't find the faster data page for this. I'm using the wrong Google, so somebody can put that in the chat. I find it that it's hard to search for. But anyway, you can use NUTTCP, and you can probably use iPerf to set up a sub-line rate UDP tests with the packets organized in bursts, and then you can kind of probe and find out what the depth of an intermediate queue is. And using this, I estimated this queue. I should say estimated rather than measured this queue at about 45 packets, it looks like. and it might just be Cisco's habitual 40 packet queue. But in this case, we were able to use flow control to change which device and interface the queue dense bursts were processed in. Ultimately, we were able to push the queue overflows to a deeper queue when they were no longer where there were no longer overflows, and there are pause counters all over the network, and it may be that there are others with a message, because every pause frame is in fact a queue crying for help. So somewhere on your network or our network, there are probably other little mysteries that can be solved by looking at pause counters. And another slide that I don't really know where to put, but so the additional space, why 9,000 byte MTU packets were more lossy than 1,500 byte MTU packets is because in that 3% reduction step queue on the ONS, a 8,000 byte payload requires 242 byte times behind it of silence in order for it to be dequeued on the WAN-Fi side. And then the smaller packets require considerably less silence. And it's always interesting, there's always this, you talk about queues and buffering and stuff, and queues are generally specified in packets. Buffers are generally specified in bytes, and packets do not behave nicely by always being the same length. So, as for Ethernet flow control and SharkBite connectors, I don't trust either one, but for some reason, neither has ever given me a reason to doubt. So, I believe flow control pause frames will make my traffic bursty or something. But what it ends up doing is extending functional coherence across devices. If you don't have it generally turned on, which I'm not suggesting that you do because it isn't perfect, but you might look at pause counters and ask why they're incrementing. Ethernet flow control isn't perfect, and sometimes what it does is useful. That's a link to the Wikipedia page, which isn't bad if you haven't really thought deeply about flow control. So there are actually two people on the call that contributed quotes for slides. One is Jim Warner and the other is anonymous. So Jim's comment, this is just a little idea of what you're up against when you start to really get down to the nitty gritty of a WAN-Fi, LAN-Fi change. It's, excuse me, you can read this later, and then you can go read that IEEE thing if you feel like you're not sleepy enough. But part 3. So burst and mitigation, the total time required to send a set of packets from an output queue is what I call the outbound wire time, which includes bytes plus the preamble plus the minimum interframe gap. The queue gets more full when the enqueued packets add to the total outbound wire time faster than dequeuing subtracts from it. Queue depth is the capacity to endure increases in outbound wire time until sufficient space-time, nothing to do with relativity, just when I say space, I mean silence or non-activity on the wire occurs when sufficient space occurs to permit queue drain. This is me writing down what I say out loud in the car when I try to figure out queuing in general. And my little, of course, my 3% reduction from LAN-Fi to WAN-Fi is unusually illustrative, because most of the time when you have a queue that's overburdened, what you have is more than one 10 gigs coming into a switch and then queuing into a single 10 gig going out of a switch, and that's harder to visualize. So this LAN-Fi WAN-Fi thing is kind of a boon. So overload bursts carry enough density to consistently cause queue overloads. For our ONS, 45 packets with it tends to pace sender packets A.K.A. to ensure sufficient space between frames, is explained kind of breezily by me in the Perf Club post, and then better in the faster data, which has been updated in the last year. There's and they tend to push you off towards fair queuing, but the fact of the matter is there's probably a lot more Linux out there today on this day, and this day in history, that's capable of the hierarchical token bucket stuff, but not of fair queuing yet, although more and more. I have a lot of Debian 8 and I don't have a lot of CentOS 7, but good reading. The faster data stuff tends to say that the scheduling from the sender is useful from a fast end host to a slower one, but the truth is, if you've got a lossy path, you can often increase throughput through the mid-pass lossy queue by ensuring that there's enough space in your stream. So, an interesting anecdote. I wrote the post on the above on perfclub.org, and somebody forwarded to somebody else. Oh, by the way, I didn't make the faster data links smaller to de-emphasize them. I made them smaller so they would fit on the slide. But anyways, somebody forwarded that post to somebody, and somebody else forwarded it to somebody else, and and it came back through the bucket brigade, and we got this message. This guy, this is kind of fun. I forwarded this to the folks in my group, and immediately piqued the interest of the group who have been, the people who have been struggling with network performance between here and etc. This struggle has been going on for decades. One of our guys decided to try a few of the suggested tweaks and immediately began seeing a significant performance improvement. He then immediately came to my office to ask me, where had I gotten this article? You mean somebody just randomly sent this to you? What for? What kind of people do you know that would just randomly send you stuff like this? And so, through the eyes of a child, it actually is kind of miraculous what you can do with packet pacing. And this is kind of the moral of the story. I mean, this is the point in me telling this group about this stuff, because many of you know more about what I'm talking about than I do. Many of you, some of you will be interested to hear it for the first time, but sometimes we don't realize that the cause of what I call the multi-Googles theory, which is that people call my office to ask me a question, which I then search on Google and give them the answer. Why don't they just search Google? And the fact of the matter is, when they don't know what something's called, or that it exists, or what form it might have if it did exist, it's invisible to them. It's hard. It's really hard to get your fingers around something when you just don't know it exists. So there's something here. There's something to be said about outreach, which I'm not going to say because I haven't really formulated it yet. So part 4. So the reason for the teaser in the abstract, the reason that you can see microsecond level bursts in a 5-minute sample MRTG graph is because network traffic is self-similar. So if you see bursts here, you've got bursts down in the mud. So this is the link in question. This is the link to Seattle, which on an MRTG graph is running about 5 gigs. So it's not congested. Why would there be packet loss? 5 gigabits high watermark apparent burstiness at 5-minute averaging. So this slide is blank. Why is that? Crap. Tell you what. Let me just call up the actual thing.
So while Alan is calling up the actual thing, reminder to type in questions as you think of them, and we will let the actual thing come back.
Okay, I'll just put this in front for a minute. So these are pause frames counted on the interfaces facing the ONSs. And there's actually a sister link to Los Angeles. And before we did this troubleshooting exercise, and before we located that lossy queue in the ONS, we always loved Los Angeles more because it was better than its sister, and prettier and more poised, and didn't drop as many packets. But the truth is, it had exactly the same problem, and for whatever reason didn't exhibit it as much. But you can see that, and I'm all messed up because I forgot what I was going to say about the slide, but you can see that there's several hundred pause frames per second, often during the day, in little bursts. It'll come on for a few minutes, and then it'll be quiet for hours, and then it'll come on for a few minutes. And this is probably a schedule of perfSONAR tests and some other choice activities. But there it is. So now I have to go back and find my, yes. So this is my blank slide, which I'll try to fix before I share the slides. And the implications of line rate at microsecond scale. So with this not very full link, why are there drops on that queue? It's because the queue fails when you have more than 9.6 gigabits per second on a scale of a few microseconds. So after this whole exercise, I got kind of interested in whether or not you could examine per packet or inter-packet timing with a Ethernet capture interface. And I was skeptical, kind of like shark bite connectors and Ethernet flow control, about whether this would work. But how do things like buffers and interrupt latency and IO weights and general quantization distort the view of packet-to-packet timing offered by a capture mechanism? Or to make a metaphor, how dirty is our window? First of all, if you're not captury, I actually used to have a Spark 10 as my desktop, which had an FDDI interface on it, and I was on the campus FDDI backbone. And so in the early 90s, I did an awful lot of looking at packets because I just could. It was very, very easy, and it was using tcpdump and the Berkeley packet filter, which is a precursor to libpcap. And it was very interesting, and it gave me a lot of experience looking at packets. And in the 20-some years since then, I've kind of learned basic truths about capturing. And if you're not if you're not a packet captury person, I'll tell you, you have to rearrange the interface, make sure MTU is set to traffic MTU or higher. You might as well just set it to the max MTU for the device. If you don't, the capture int will discard what it sees as giants. So if you interface comes up at 1500 bytes MTU and you got a 9000 byte MTU link that you're looking at, you won't see very much. Make sure all types of segmentation offloading are disabled, because that will otherwise you'll capture 65,000 byte packets and you'll wonder what the heck is going on. Checksum offloading should probably be turned off. It depends on what you're looking at. The worst thing about leaving checksum offloading on is that the Ethernet NIC may discard packets that when it fail the CRC, and you will never see them. And also, you probably turn it all off, and turn off auto negation if you can get at it. So this is the tab setup. If I'm going to look at per packet timing between packets, you want nothing between you and the packets. So I had to, and the following 10 slides or so are all about evaluating whether what I'm seeing through the capture interface is in fact what's happening on the wire or on the fiber. So the thing about optical taps is they provide you with 2 strands out, and the strands each have a eastbound packets on one strand and westbound packets on the other strand, and normally you feed them into a switcher and aggregator and get one stream, but of course you don't want to do that here because you want to see the actual time relationship. So pcap, NICs, and timestamps. Normally pcap apps just use system time when they get a packet, although more IEEE 1588 precision time protocol compatibility is changing this. Or I should say the pcap apps still use system time, but many of them have the capability to request hardware time from the NIC, and there are more NICs providing hardware time with IEEE 1588. This adds or subtracts a variable mystery interval from the actual packet arrival time. Intel NICs offer a timestamp from the NIC, which is referred to as software time, but is much more precise than system time if your app can use it, which is a compile time thing, and if you ask your app to, if you invoke your app to ask for it, which is a runtime thing. Of course, other schmancy NICs are available to do hardware timestamping. I didn't really go out and get a proper list. I've seen many other NICs that are kind of capture optimized, but the old Whinery COM, which many of us have because it was one of the 10 gig NICs that was available at a reasonable price 10 years ago, they offered extra stuff that you could license from them and do better timestamping and more capture stuff. New Whinery, which is CSP, has bought the Whinery product line and it has a capture specific line of cards called ARC, which there's a link to there. And there are, of course, others, which I can't think of. I won't go off the reservation. So when I'm invoking tcpdump, for instance, you have to say you want timestamp precision equals nano, which is only there if you compiled it there, and it's only available from the NIC if the NIC provides it and the NIC driver provides it. And then you do -J adapter unsynced, which is a timestamp type from which you can say adapter, you can say adapter unsynced, you can say system, you can, there's a couple of choices, a couple other choices. -I, Ethernet 0, the 0 copy version of Ethernet 0, and I'll get to what 0 copy means within a slide or two, and then you write your capture file. This is specially compiled tcpdump more later. T-Shark, I tried to do some of this with T-Shark, and T-Shark was flaky on, gosh, I have a note about this. It was doing large numbers of timestamps and hardware timestamping. It flaked out. It would get lost and run a big load. And that was a year ago. It may have improved since then. So there's a thing called pfRing, which is available from Luca Deri and the NTOP people. And pfRing is a capture optimized Ethernet driver socket, which allows you to do higher capture rates. It allows you to get better time resolution. And there's a second version, which is pfRing ZC, which skips kernel involvement altogether to get packets into user space. There's a link to it there. Licenses are available at no charge to educational institutions. I actually have a license, but for this exercise that I'm about to talk about, I just worked with the 5-minute demo limit. So if you download it, if you do the git clone and want to mess around with pfRing, you can actually capture for 5 minutes repeatedly ad infinitum and not run up against the license problem. So you can play with it quite a bit. And most of the things I did took about 10 seconds. So, so using pfRing ZC minimizes that mystery interval between packet arrival and timestamp recording. pfRing git clone includes userland apps, including the appropriately spiked versions of tcpdump, and also a thing called end to disk, or for network to disk, a capture app which has, wait for it, burst detection and logging. So I really should have a series of slides about how wonderful end to disk burst detection and logging is, but I don't, because it's one of those things where the the glossy high-level explanation is all you can find, and getting down to what the parameters actually mean in detail is a little tough, and I haven't done stuff with that yet. But I would really like to get it going, turn on my license and get it going and run it on a link, and you can log bursts of a certain density. Also, just a random thought, I've spent a certain amount of time using my Google to try to figure out how to capture pause frames, and I've not succeeded in doing that yet. The only indication that we have that pause frames exist is that they're kind of like neutrinos. They make counters increment. They get absorbed by the silicon before you can see them. So, excuse me, I'm gonna have another cough drop. This is not a time series. This is a packet sequence series, meaning the x-axis is the number of packets in a sequence. So the index of each packet's in the sequence. This is a NUT TCP UDP test with a rate of 500 megabits. It should be RI 500M, but rate of 500 megabits. And you can see that the interframe, and what is plotted is the interframe gap. And you can see the interframe gap tends to bunch. All the power is right around 100,000 nanoseconds, 100 microseconds. And there's some spreading when there's resource contention in the sending host. And you can see that it's actually not a bad representation, I say in retrospect, but this is the plain vanilla Linux distro Ethernet driver looking at interpacket gaps. And it's not bad. It shows you a reasonable representation. But if you do the same thing through pfring zero copy, you get a lot more detail. And you get some other features. Bears a look. Of course, it's not the same test. It's the same invocation run at different times and captured with different stuff. So this is the frequency histogram from the vanilla driver, Linux distro driver, and this is the frequency histogram from pfring ZC. So you can actually see that it does get rearranged quite a bit. This is almost like a sideways histogram because it shows the occupied bands of frequency in interframe gap along the packet sequence, but it does not show you the amplitude of each of the bands, and these do. So I'm not going to get bogged down on that. So just to look at what I call the resource contention intervals in the pfring ZC graph, we'll zoom in on what the red thing is poorly trying to represent an arrow. And this is what you see. So within that bunchy resource contention stuff, what you've got is about every 12 packets, the packet gap jumps from about 5 microseconds to about 1 millisecond, because if you hadn't noticed, these vertical scale is log scale, and which is quite a jump, but it's also not that bunchy. The low number is nothing to threaten a queue in terms of filling it up and making it overflow, because 5 microseconds is a long time in 10 gigabit Ethernet universe. But the 1 millisecond is a pretty large period of silence. So here's another capture. This is the packet sequence with the burst feature of NUT TCP, and you can see, of course, that there's this at 10 million nanosecond gap is the interburst gap. So the bursts happen, And notice that the bottom of this is at about 1,000 nanoseconds. So about a microsecond is about the shortest interframe gap I'm seeing. So the bursts that NUTCP is producing are not really that tightly bunched. But you can see there's a certain amount of power right across the top in the inner burst gap. And this is just the histogram version of the same thing, which is rescaled, so you don't see as much detail as you did on the previous histogram. So here's the obvious culmination of all this. I set up that hierarchical token bucket output queuing pacing on the sender, and at 500 megabits. I told it to limit the output at 500 megabits. And then I ran a test with 600 megabit requested rate and 100 packet bursts. And you can see that there's no notable interburst gap showing up here at all. And the actual result, the throughput result from NUTTCP was about 512 megabits. And so this looks more like this with no burst looks more like the one that's running through the token bucket than the one with the bursts without the token bucket. So it really does kind of clamp down on things and it spreads them out. There was no loss in this test, so that stuff worked reasonably well. Just for fun, I did a TCP test, and this is what it looks like in terms of interpacket gaps. Of course, there's a lot more going on with the TCP state machine and the interaction between the two ends. So but there isn't that resource contention blur that you see on the wide open UDP tests. And this is, unfortunately, I didn't have a single mode SFP plus to put in my capture interface. Otherwise, I could have gone right on the wire because we have an optical tap in that Seattle link. I could have gone right on the wire and listened to the Seattle link and look at live traffic and see what kind of strata you get in your interframe gaps. But do note that this thing scaled to 1 nanosecond as the bottom of the graph. So the other one was 1,000. And so there are considerably tighter groups in this, probably from some queuing on the MX480 when it dequeues packets, as fast as it can. So it's putting them right on there end to end. But it's not getting, of course, it isn't overflowing that queue anymore on the ONS. You also don't see, it's not apparent to me exactly what you would be looking for pause frame stuff, which actually the minimum pause that can occur is 64 byte times. So using that, maybe I could isolate that. But there's more to be looked at. That's the histogram view of the live traffic, which is actually a little more spread out, a little more scattery than the UDP tests. So I've reached the end of my slides. I could probably talk for a lot longer if you want me to, but let's see. Did we get any? Are there any questions?
There were a couple, but Eli has been fielding them, including finding the link to the faster data thing. So that is in
thanks.
there. And also a question about interframe gap. So very fascinating. Thank you again for going over this. This was my personal request. I really wanted Alan to talk about this because I think this is a great use case. I want to know more about pause frames because I think your comment sort of mimics a little bit about what I've experienced. I've never been able to physically capture them either. You only see the outcome of what happens when you get there. So how challenging does it make debugging these things when you start to experience that those are coming in? I mean, it typically just turning it off on one end usually helps, but it doesn't really fully alleviate the problem from your example, it looks like.
Right. Or turning it on.
Yeah.
Yeah, if you read that Wikipedia page, it touches on a couple things. Ethernet flow control is the title of the page, and it actually touches on a couple of problems with the flow control as implemented, but doesn't mean it's useless. So in a situation like ours, it actually saved the day. So are there unanswered questions yet? Let me see. I mean, Eli's probably way ahead of me on most of this stuff.
Well, Eli has one now. You can probably just unmute yourself and ask Eli. You have the keys to do so.
Okay. Can everybody hear me okay?
Yep.
Yeah, okay. Thanks, Alan. This is totally in the kind of space that I've wanted to get into for a while, and I've never managed to put it all together. So this is fantastic. One of the things that I wanted to do for a while is characterize the burstiness of either different NICs or of different kernel different versions of the Linux kernel or things like that, because that has impact. I mean, as you just very well described, right? That has impact downstream on shallow buffers or fan-in or different things like that. And so, how well would the test rig that you have set up here work out for doing that sort of testing and characterization?
I think that I really want to look at N2Disk and pfring ZC together, because N2Disk has this thing where you can tell it to log bursts, but you have to specify a time window for bursts. And then so you really got to get your mind around what kind of burst is dense enough to be a problem and what kind of burst isn't. So you can tune it to tell you about the bursts that you want to know about. And also the flip side of that is you can see what kind of burst causes a problem. You could run a throughput test between two perfSONAR hosts, and some unknown mystery queue somewhere out in the wild is dropping your packets, but you can look at exactly what size and what density of burst makes that happen, and then if you stretch the bursts out when it stops happening, I don't know if that helps you locate the queue, but it certainly helps you optimize the path, which is, if it's Friday night and you want to move some data, the token bucket or fair queuing thing is a panacea.
Yeah, I mean, one of the things that I'm looking at, I mean, at the moment actually, is I have something I'm working on debugging where there's a DTN cluster, the individual hosts of which have 40 gig interfaces, moving data to a DTN cluster, the individual hosts of which have 10 gig interfaces. And the speed step reduction is at the 10 gig host facing switch port, and those queues are tiny.
Right.
And so, the sort of thing that would be really slick would be to be able to say, okay, well, how do I dink the inner frame gap on these transfers to get it below whatever is going to blow out that switch queue. And for a large production facility, right, getting that sort of thing into place for one destination is probably not, realistic, but it's still, useful to be able to characterize. So anyway, that's the sort of circumstance in which I'm thinking of it, right? It's like, because we're in this transition between 10 gig and 40 gig DTNs, and soon to be 25s and 50s, but we're in another point in the cycle, right, where we've got all these mixed mode things where we have not dissimilar speeds talking to each other, and it's causing some problems.
I've often wondered if you built like a high performance Linux box with two good NICs in it, if you couldn't build yourself a network buffer to put right in front of a shallow queue switch to handle the queuing on behalf of the switch. And,
yeah, I bet you could do that.
And I haven't gotten around to that because sometimes people want me to do my day job.
It's
but but it's a good lightning talk if you do it. So.
All right, we have a question from Eric. TCP stack I've looked at will continue to emit packets while the window is open. Before relinquishing the kernel thread, might be possible to instrument the kernel to see this burstiness.
Right, that's a good point.
And Lucas has, I'm not aware of familiar network topology and also perfSONAR, but have you guys planning to work routing switching using DPDK compliant NICs?
That comes up in the, if you read the PF ring stuff. But I don't know. You PSNet guys are more, have a broader view. Have you heard that coming up?
Yeah, I mean, so there are some people who are looking at SDN soft switches to run on Linux boxes, and they're doing DPDK implementations of those. And so like for example, the network buffer box that you were just talking about, right? The dial and interframe gap sort of thing. That might be a good candidate for a DPDK implementation. I personally haven't done anything with that. I know some people who have, and a bunch of their work is proprietary, unfortunately. But it's something that I think has some promise.
All right. Any other questions that people have? We can pause for a minute here, and I'll thank Alan again. And when you do update your slides, just send me a copy, and I'll make sure those get posted.
I'll make sure all the pictures appear before I send them to you.
Well, that's good. Well, I had a boo-boo too. My Zoom session catastrophically failed 15 minutes in, but I got it connected quickly again, so there's going to be a little bit of a gap in the recording.
Okay.
But hopefully it didn't drop all of your sage wisdom. So Ryan has one last comment here. 40 to 10 gig regarding Eli's comment about that. Wouldn't link speed signaling go a long way to alleviate at least some of the issues here? Similar to PMTUD, but for end host DTN link speeds.
Yeah, if we could do that, if we could